you hear me? Hello?
Yes, you're audible, but little louder, please.
Hello, can you hear me clearly now?
Yes, good. Please proceed.
Oh, thank you. My name is Opeyemi Lateef Usman. I'm speaking live and direct from Research Center for Cybersecurity, Faculty of Information Science, Faculty of Information Science and Technology, University Kebasan, Malaysia. The title of our paper is Efficient Neuroimaging Data Security and Encryption using pixel-based Homomorphic Residue Number System. Yeah, the presentation outline from introduction down to references. I move to introduction. Neuroimaging data sets such as MRI scan, CT scan, PET scan, EEG scan can be used as a diagnostic tool for certain neurological disorder and learning disability, such as dyslexia, autism, and attention deficit hyperactivity disorder, because they contain certain neurobiomarker features that allow the researchers and the medical luminaries to visualize and analyze the anatomical variation in the brain component, particularly in the left hemisphere of the brain. And due to the sensitivity of these data sets and coupled with recent increase in the generation of this kind of data sets and deployment of advanced machine learning and deep learning model through cloud deployments, has resulted in the need for privacy and confidentiality protection. Consequently, the development of privacy-preserving classification framework using the concept of homomorphic encryption becomes imperative. Currently, the algorithms that are used for securing medical images along the transmission channel do not consider cloud-based classification because they have distorted the pixel location in the key regions of interest, and this leads to inaccurate and unreliable prediction. In this paper, we have presented a novel approach to securing neuroimaging datasets using a homomorphic privacy-preserving framework based on residue number system fully homomorphic scheme. The proposed neuroimaging encryption and decryption algorithm are analyzed with respect to the moduli set 2 raised to power n minus 1, 2 raised to power n, 2 raised to power n plus 1, which has been proposed in our previous paper for this purpose. The concept of homomorphic encryption is that the cloud server is able to perform certain arbitrary computation on the encrypted dataset without having to decrypt it. For instance, when user encrypts integer 5 and 12, maybe integer 5 is encrypted to polynomial P1 of S, and integer 12 is encrypted to polynomial P2 of X. And the cloud server perform homomorphic addition on the encrypted data to obtain polynomial P3 of S. If user is able to decrypt the result to 17 as if the computation was performed using the raw data set, then homomorphic encryption has ensured. And it has two properties depending on the kind of operation that is performed. It is additive homomorphism if the operation is addition, and it is multiplicative homomorphism if the operation is multiplication, with multiplicative homomorphism generating more noise than the additive homomorphism. Concept of residue number system and residue number system fully homomorphic scheme. Residue number system is a non-weighted number system that allow an integer to be represented using an n-tuple of residues based on the used pairwise relatively prime moduli. Assuming M denotes the moduli set, then M is a set comprises of module labeled M1, M2 up to Mn, in which the greatest common divisor between a pair of moduli must be 1. Equation 3 defines the system dynamic range capital letter M, which is the product of all the modules. So, for instance, if we have an integer capital letter S, which is a member of a set of natural number within the ring of M, the dynamic range, in RNS, this number X can be represented using in its module as small letter x1, x2 up to xn using equation 4, where small letter xi is equals to capital letter Si modulo mi. And the small letter Si are the residues. The proposed methodology. In the proposed methodology, 3 operations are inevitable. The first one is pixel decomposition. In the neuroimaging data sets used, the pixels, each neuroimage is decomposed into its stream of pixels. That's the first operation. And if a neuroimage is represented by I, then its pixel will be represented by x1 up to xn. Then the next stage is the encryption stage. In the encryption stage, we have the encoding of the pixels with respect to the moduli set. Then the key parameters will be used along with the large n prime number to generate the cipher pixels, while the cipher pixels will be concatenated to obtain the cipher neuroimage. For the decryption process, the n prime inverse is first of all obtained from the cipher neuroimage. Then this is decomposed into its cipher pixels, and the cipher pixels are decoded to obtain the residues, while the residues are concatenated to obtain the neuroimage datasets. This is the simplified algorithms. In the encryption algorithm, we use parameter n, k, p, rm, and n. And the input neuroimage will be I. We have as many as neuroimages as possible, where n is the value that is used to obtain the value of moduli set, with the condition that the value of n must be greater than or equals to 3. Say, for instance, if we put our value of n to be 4, then the first moduli channel will be 7. The first moduli channel will be 15. The second one will be 16, while the third one will be 31. So, and this is used to generate
Mr. Lateef Usman, sorry to interrupt. Please be a little fast.
Okay. Okay, thank you. So, and this is used to generate the encrypted residues from where we obtain our cipher neuroimage. So the reverse is the process, but in the reverse approach, we adopt an algorithm, we make radical conversion algorithm in the reverse approach. So the experimental result and discussion. So we perform the visual inspection of both the real neuroimage, plain form, and the cipher form. So there we see that there's no similarity between the pair. Also, we try to analyze the encoding size, that is the size on the disk. We compare the size of the plain neuroimage and the cipher neuroimages on the disk. We observe that the proposed algorithm is able to reduce the size of the cipher neuroimages by an average of 62%. So we also conducted some security analysis, include histogram analysis as shown in figure 4. There is no, there's the histogram of the plain neuroimage and the cipher neuroimage is completely different. We also check some the key sensitivity analysis. We see that by the time we alter any of the key parameters used the cipher neuroimage does not decrypt back to the plain neuroimage. We also perform the correlation of the adjacent pictures in both plain and cipher neuroimages, and we found low correlation coefficient value. In conclusion, this paper presents the security model and analysis of cipher neuroimages generated by the RNS fully homomorphic scheme, which was used in our previous study to model homomorphic residue number system convolutional neural network for privacy-preserving classification tasks. The neuroimage encryption and decryption algorithm are based on the powerful encoding and decoding strengths of residue number system PCB stream encoder and decoder with respect to the moduli 2 raised to power n-1, 2 raised to power n, and 2 raised to power n plus 1 minus 1. The proposed scheme can conceal and recover plain neuroimage without sacrificing inherent neural biomarker features. The experimental results also show that fewer number of bits is required to represent the cipher itself and cipher images. Finally, the result also shows that the proposed RNS fully homomorphic encryption scheme is resistant to statistical attacks such as histogram, key sensitivity, and outperform the present state-of-the-art homomorphic CNN. Thank you.
Thank you, Mr. Usman. Any questions from the audience?
Have done security analysis and space complexity analysis in isolation. What in terms of security and space complexity and time complexity, how your proposed approach is better than existing approaches? Actually, you have done security analysis in isolation. What please suggest how this proposed approach is better in terms of time complexity, space complexity, and security. Thank you.
Okay, thank you for your question. You see, the security analysis we conducted is security in terms of key space. Here we try to use the key length suggested in the data encryption standard. We use 128 bits, and to decrypt this, the attacker would take more than 1,000 years. Even if we adopt the 256 bits recommended by the National Institute of Standard and Security, which is using the advanced encryption standard. So it takes longer time to decrypt. The complexity of the design, because the algorithms spend longer time during the decryption due to the interdependency of mixed digits that is ensured in the computation of the mixed radius conversion process. Because mixed radius conversion process has a lot of steps embedded within it, so the asymptotic complexity of that is big O of n raised to power 3, because that is where the algorithm takes longer time. Here we can say the decryption algorithm sacrifices space for time complexity. Thank you.
Thank you. Thank you.